Have you ever held a sapphire in your hand? That brilliant blue stone sparkling under the light isn't just a gem, it's the product of millions of years of nature's work and decades of human effort. Today we're taking you deep inside the world of supergiant sapphire mining, from rugged mountains in Montana to cutting-edge processing facilities, to see how one of the world's most valuable gems is found, extracted, and transformed into treasures that last for generations. Before we dive in, don't forget to like, subscribe, and hit that notification bell for more fascinating behind-the-scenes journeys of how the world's most valuable materials are made. Sapphires aren't just beautiful stones. They're a type of corundum, a mineral made of aluminum oxide, and they rank 9 out of 10 on the Mohs hardness scale, just under diamonds. What makes sapphires special is their trace elements. Tiny amounts of iron and titanium give them that deep, royal blue color. Other trace elements can make them pink, green, yellow, or even colorless. In the US, the most famous sapphires come from Montana, a state often called the Treasure State. Here, sapphires were first discovered in the 1860s by gold miners. They weren't looking for gemstones, they stumbled upon them while panning for gold. But soon, sapphire fever spread. By the late 19th century, the famous Yogo Gulch deposit was discovered. Yogo sapphires are legendary, prized for their uniform cornflower blue color, exceptional clarity, and the fact that they don't need heat treatment to enhance their beauty. From royal crowns in Europe to engagement rings in the US, sapphires have always carried an air of mystery, wealth, and prestige. Imagine standing in the wide-open landscapes of Montana. Rolling hills, gravel bars along the Missouri River, and rugged gulches carved by ancient glaciers. This is sapphire country. Sapphires are typically found in placer deposits, where ancient rivers carried them down from eroded mountain rocks. Over time, the heavier sapphires settled in gravel beds waiting to be discovered. To locate sapphire-rich areas, geologists study the land, analyzing sediment layers and rock formations. In modern mining operations, giant excavators and dredging machines are used to scoop up tons of gravel and sediment. Every shovelful could contain sapphires, but the odds are small. On average, miners might move hundreds of tons of rock to find just a handful of quality gems. That's what makes sapphire mining both a gamble and a wonder. Now let's head inside a supergiant mining plant. Massive bulldozers dig up sapphire-bearing gravel, sometimes working through layers that are millions of years old. The raw gravel is loaded into washing plants. High-powered water jets separate lighter material from heavier stones. Sapphires, being heavier, settle at the bottom along with other dense minerals. Workers and machines sift through the concentrate, looking for flashes of blue, green, or yellow, the telltale sparkle of a sapphire. The excitement of finding a sapphire hasn't changed much since the gold rush days. Each discovery feels like unearthing a hidden star from the earth. A rough sapphire doesn't look like the sparkling gemstone you see in jewelry stores. It's often cloudy, irregular, and dull. Here's how it's transformed. Grading. Experts examine the rough stone for color, clarity, and size. Cutting. Skilled lapidaries use diamond-tipped saws and precision machines to cut the stone. The goal: maximize brilliance while minimizing weight loss. Polishing. Facets are polished to perfection, unlocking the sapphire's fire and sparkle. Heat treatment. Optional. Some sapphires undergo controlled heating to enhance their color. But remember, Yogo sapphires from Montana are naturally beautiful and rarely need treatment. The result? A gemstone that can fetch anywhere from a few hundred to tens of thousands of dollars per carat. While sapphires are famous in jewelry, did you know they also power modern technology? Industrial sapphire glass. Scratch-resistant, used in watch faces, smartphone screens, and scientific instruments. Laser technology. Sapphire crystals doped with titanium create powerful blue lasers. Electronics. Thin sapphire wafers are used in semiconductors and LED manufacturing, so sapphires aren't just about beauty. They're also about science and progress. Behind every sapphire is a story of people. In Montana, mining towns grew around sapphire deposits. Families worked the gravel bars together, passing down stories of luck and discovery. Lapidaries, the skilled craftsmen who cut and polish gems, dedicate years to mastering their art, turning rough stones into dazzling treasures. Jewelers and designers then carry the final product to customers around the world, where sapphires symbolize love, loyalty, and wisdom. Mining also brings challenges, balancing economic opportunity with environmental responsibility. Modern operations focus on land restoration, water recycling, and sustainable practices to protect Montana's natural beauty. Think about this. A sapphire you might see in a ring today could have formed over 500 million years ago, deep within the Earth's crust. From its birth under extreme heat and pressure, to its discovery in a Montana gravel bed, to its transformation in a cutting workshop, that journey is nothing short of extraordinary. Thanks for watching, and until next time, keep discovering. Every day, millions of machines quietly keep the world running. Electric cars, elevators, washing machines, industrial robots. At the core of nearly all of them lies a single essential component: the electric motor. But what powers the motor itself? How is it made, and where do the raw materials come from? In this documentary, we step inside a state-of-the-art facility to uncover the full journey, from recycled metal scraps to precision-engineered electric motors. It's a story of molten metal, spinning copper coils, cutting-edge robotics, and sustainable innovation. You'll witness how scrap metal is recovered, melted down, and reshaped, and how advanced manufacturing techniques transform these raw elements into the motors that drive modern life. This isn't just about engineering, it's about the future of power, production, and the circular economy. This is the incredible manufacturing process of electric motors and the metal recycling revolution behind it. Every electric motor begins its life not on an assembly line, but in the scrapyard. Tons of discarded metal, from old appliances, demolished vehicles, and industrial waste, arrive at recycling centers every day. What once was broken and forgotten is now seen as raw material for the next generation of machines. The first step is sorting. Using powerful magnets, conveyor systems, and infrared scanners, metal is separated by type: ferrous from non-ferrous, steel from aluminum, and copper from brass. Precision is critical. Even a small impurity can affect performance in later stages. Once sorted, the metals are cleaned of dirt, oil, and coatings. Then they're shredded into smaller fragments and sent to furnaces where they're melted down. Aluminum melts at around 660 degrees Celsius, copper at over 1000 degrees, and steel at an even higher temperature. Inside the massive induction furnaces, the scrap metal becomes molten, glowing with intense orange heat. Impurities rise to the surface and are skimmed off as slag, leaving behind purified metal, ready to be reborn. The molten metal is cast into standardized forms: rods, sheets, or billets, depending on the motor component it's destined to become. Aluminum may be rolled into housings, copper into winding wire, and steel into rotor shafts. Before these materials even reach the motor assembly line, they've already been through fire, force, and filtration. It's a transformation few see, but one that underpins every step of modern manufacturing. The journey from junkyard to high-performance component has only just begun. At the center of every electric motor are two vital components: the stator and the rotor. Together, they form the beating heart of the machine, converting electrical energy into mechanical motion with remarkable efficiency. Once the raw materials have been purified and shaped, they move into the precision engineering phase, where each part is carefully manufactured to tight tolerances. Let's begin with the stator, the stationary part of the motor. It typically consists of laminated steel sheets stacked together to form a hollow cylinder. These sheets are stamped with slots that will later house copper windings. Lamination is crucial. By stacking thin layers instead of using a single block of metal, the motor reduces energy loss caused by eddy currents, improving overall efficiency. The stator core is placed in an automated winding machine. Here, insulated copper wire, usually made from 99.99% pure recycled copper, is wound into tight, uniform coils that fit into the slots. These coils are not randomly wound, they follow a precise configuration based on the motor's design. Whether it's a three-phase industrial motor or a small DC motor for a household appliance, the winding pattern defines how the magnetic field will be generated. After winding, the coils are dipped or sprayed with varnish, then baked in industrial ovens. This insulation process ensures that the wires remain fixed and protected from moisture, vibration, and heat during operation. Next comes the rotor, the rotating part of the motor. Depending on the type of motor, it may consist of solid steel shafts, laminated cores, or even cast aluminum squirrel cage designs. In induction motors, for example, molten aluminum is injected into molds around a rotor core, forming conductive bars that interact with the magnetic field from the stator. Balancing is critical at this stage. The rotor must spin at thousands of revolutions per minute without wobbling. High-precision machines check for even the smallest imbalance. If necessary, micro-adjustments are made by shaving material or adding weights to achieve perfect symmetry. Bearings are then installed on each end of the rotor shaft. These reduce friction and allow smooth rotation while also handling the mechanical loads during operation. Depending on the application, the bearings might be sealed, ceramic, or even magnetic for ultra-low resistance performance. Once the stator and rotor are completed, they undergo separate quality control inspections. Electrical tests check for coil resistance, insulation integrity, and potential short circuits. Mechanical tests verify alignment, dimensional accuracy, and overall structural soundness. It's only when both components pass all tests that they move to the assembly phase, where the motor will finally take shape. Building stators and rotors is not just about metal and wire. It's about precision, durability, and an invisible choreography of electromagnetic forces. Because inside every electric motor lies a symphony of motion, and it all starts with these two elements, engineered to perfection. With the stator and rotor meticulously prepared, it's time to bring the electric motor to life. The assembly process begins in a clean, organized line where each component is carefully fitted together. The stator is mounted into the motor housing, a protective shell made of cast aluminum or steel, often die-cast from recycled metal. Next, the rotor is gently inserted into the center of the stator, ensuring a precise air gap between the two. This tiny space, measured in fractions of a millimeter, is critical for the motor's efficiency and torque output. Once aligned, end bells, bearing caps, and cooling fans are installed. In larger motors, sensors are embedded to monitor temperature, vibration, and performance in real time. Now comes the moment of truth, testing. Each assembled motor undergoes a series of rigorous quality control checks. First, it's powered on and run through various speed and load conditions. Engineers monitor electrical consumption, heat buildup, and vibration levels. Any irregularities, such as excess noise or current imbalance, trigger a full diagnostic. For motors used in sensitive environments like aerospace or medical devices, testing becomes even more intense. Motors may be subjected to simulated environments, high altitudes, extreme temperatures, or continuous 24-hour runs to validate durability. Only motors that meet or exceed performance standards move on to final packaging. Those that fail are flagged, disassembled, and either corrected or recycled. Every motor that leaves the line is tagged with a serial number and logged in a database for traceability. Whether it's destined for a factory floor, an electric scooter, or a wind turbine, one thing is clear. Its journey from scrap to spinning power is nothing short of extraordinary. Every factory generates waste, offcuts of aluminum, worn-out copper wire, broken bearings, and defective components. But in modern manufacturing, waste is no longer the end of the line. It's the beginning of something new. Metal recycling is not a side process. It's a central pillar of sustainable industry. In the electric motor factory, a dedicated section is designed solely for collecting and processing metallic byproducts. The process begins with collection. Every scrap, from a trimmed copper wire to a rejected steel shaft, is sorted and deposited into labeled bins. Workers and machines collaborate to separate materials with precision. Copper, aluminum, and steel are never mixed. Even slight contamination can compromise the integrity of recycled alloys. To speed up sorting, advanced detection systems are used. Induction sensors, X-ray fluorescence, XRF scanners, and automated vision tools identify metals based on density, conductivity, and chemical composition. These high-tech systems reduce error and maximize recovery. Once sorted, the metals are prepared for shredding. Large industrial shredders chew through hardened parts and tangled wires with ease, breaking them down into uniform chunks. The goal isn't just reduction, it's surface area. The smaller the pieces, the easier it is to melt and purify them later. After shredding, magnetic separators remove any ferrous contaminants from non-magnetic metals. Then eddy current separators isolate aluminum, and density-based systems sift out copper. The result is a clean, sorted stream of valuable raw material, ready for resmelting. But recycling doesn't stop at sorting and melting. Inside the furnace, these metals undergo a second transformation. Recycled copper is refined to 99.99% purity, good enough for electrical-grade wire. Aluminum is cast into ingots or extruded into new housing components. Steel is alloyed and rolled back into rotor shafts and fasteners. The energy required to recycle metal is a fraction of what it takes to mine and process virgin ore. Recycling copper, for example, uses up to 85% less energy than mining. That translates into lower emissions, reduced environmental impact, and more sustainable production overall. What's more, metals can be recycled infinitely without losing their core properties. Unlike plastic or paper, which degrade over time, copper, steel, and aluminum retain their strength, conductivity, and resilience through countless cycles. This circular approach turns the factory into a closed-loop system. The waste of today becomes the resource of tomorrow. Scraps are reborn as stators, rotors, casings, and eventually, as fully functional motors powering the next generation of devices. Recycling also protects supply chains from raw material shortages. As global demand for electric motors grows, driven by electric vehicles, renewable energy, and automation, reliable access to copper and rare metals becomes crucial. Recycling helps bridge the gap. It's not just good economics, it's smart engineering, and a powerful way to align manufacturing with environmental responsibility. In the end, every spinning motor tells a deeper story, not only of precision mechanics, but of a cycle that keeps resources in motion, just like the rotor it powers. At the heart of metal recycling lies one of the oldest and most awe-inspiring processes in human industry: melting. In this chapter, we enter the fiery core of the factory, where scrap metal is reborn in furnaces hotter than volcanoes. Once sorted and shredded, metals are sent to their respective smelting stations. Each type of metal requires different treatment. Copper is melted in induction furnaces that reach over 1,100 degrees Celsius. Aluminum melts at around 660 degrees Celsius, while steel demands temperatures exceeding 1,500 degrees Celsius. These furnaces are no ordinary ovens. Using electromagnetic induction, massive coils generate high-frequency currents that heat the metal rapidly and evenly. Inside, the shredded pieces glow and liquefy, forming a swirling pool of molten metal. But before this liquid metal can be reused, it must be purified. Impurities, known as slag, float to the top of the molten bath. These can include oxides, dirt, old coatings, and traces of other metals. Operators add fluxes, such as borax or limestone, which bond with the impurities and help them separate more easily. The slag is skimmed off the surface and collected for further treatment or safe disposal. For metals like copper, further electrolytic refining may follow. In this process, an electric current passes through a copper solution, causing pure copper to deposit onto cathode plates while impurities fall away. The result is copper so pure it can be used in the finest electrical components. Once purified, the molten metal is ready to take shape again. It's poured into molds, either to form ingots, rods, billets, or sheets, depending on its intended use. Aluminum may be cast into large blocks for machining into motor housings. Copper may be extruded into long wire rods that will later be drawn and insulated for motor windings. Steel is often cast into billets, then sent to rolling mills where it's shaped into shafts, laminations, or fasteners used in motor assemblies. Throughout this process, temperature, viscosity, and cooling rates are tightly monitored. Too hot, and the metal might develop cracks during cooling. get too cold, and it may not flow into molds properly. Precision ensures structural integrity, electrical performance, and long-term durability. After cooling, the solidified forms are trimmed, cleaned, and inspected. Automated scanners check for defects. Some pieces are sent for machining, while others go directly into inventory.